remember to do a flywheel to prevent that. Okay, for going over to the negative cycles. Okay, similarly again, okay, also when you apply it to any the DC motor, okay. Okay. So now we come to the okay, one of the major application okay, of this control rectifier is actually to control the DC machine. All right. Of course, it's a high power industrial DC motor. It's not the 1 liter small one we use for the toys, or the small motor they use for your car mirror controller or your CD-ROM drive. Okay, not that type. Okay, we are talking about like 10 horsepower and so forth. So it's industrial based. I believe you all have studied electrical machine, right? So these are a few configuration that the DC machine okay can do. So of course one of them is serial. Okay, that means the field coin and the armature coin are connected in serial. Okay, and of course, which is not least here is some of them are using a permanent magnet, okay, to replace the field. However, the problem is that you have no control on the field's magnetic, okay. And then for big motor, right, and if you want to have this permanent magnet, okay, it's not feasible lah, because it's too costly, okay. And then as we know that permanent magnet, right, are made out of rare material. Okay, so to solve this, okay, we replace that with a field coin. And of course, the DC machine can configure in series, in shunt, okay, or compound, both series and shunt. And of course, the last one will be separately excited. Okay, those you can see commonly used in the industry is separately excited. Okay, that's mean the armature and the field coin are powered and controlled separately. That will give you the best control you can, okay, because you control them with a separate source. And of course, the other one for simplicity is the series. So these two types are the most common you can see in the industry. This one, you just need to have one control rectifier, which will apply to both the field and armature and the control at the same time. Okay, the speed and torque you control at the same time. But you cannot control like individual torque and speed, okay, because they are connected in series. If you want to control, more control, like, okay, I want certain torque and certain speed, then you need to use a separately excited motor. Okay, so these are just some of the very basic, what we call principles of the series DC motor. Okay, so this is for the series. Okay, as we know that the armature and the field are connected in series. Okay, the red color box is the electrical side and the blue color box is the mechanical side. As we know that machine, right, electrical machine or motor is to convert electrical energy to mechanical energy. And the key things, okay, of the transformation from the electrical to the mechanical is the EG. EG is a back EMF, okay, and EG consists of kV. Okay, kV is the motor constant voltage. Okay, it's a motor constant voltage. So this is the key, okay, and a lot of the motor, right? And when you come to the mechanical side, right? Okay, so this is the torque. Okay, and this KT. Now, a lot of time we will assume KT and KV should be equals the same. Okay, unless it's a very delicate motor that you will have a different value of KV and KT. So for simplicity, we will make KT and KV the same. So basically, it's basically just governed by Ohm's law. All right. So your VA, right, is your RA plus RF multiplied by the current. Okay, and then plus, okay, these are EG. EG is the kV, which is the constant, okay, and your omega, which is the speed, okay, and of course, the IA or IF depend on your configuration. All right. And then once we have the torque, okay, on the mechanical side, right? And yeah, the omega, which is the speed, okay, will be defined by the wattage armature, okay, minus by the RA plus RF multiplied by RA divided by kVIF. And then, of course, with this one, okay, and the torque, you can actually calculate the mechanical. This power is not electrical power, it's a mechanical power of the motor. Okay, so they are in watt. Of course, you can convert them in horsepower. So that is a very basic, yeah, you see in all textbook. Okay, and of course, in reality, the KT and the KV is the key value to determine how well is the motor DC machine is operate. Usually they don't provide all those manufacturers. All right. Okay, and of course, like I said, you have a separately excited. Okay, now this is another commonly used configuration. In fact, the equation is the same. Only the what we call this the VA side, we don't have the RF and the IF. Okay, so IF will be only taken here, where the kV, okay, convert from electrical energies to the mechanical energies. So the difference is that you only have this separate coin, okay, that will give you a VF equal to RF multiplied by the IF. So yeah, basically you see these are all Ohm's law, except the EG, back EMF, that you have to deal with the mechanical part. As long as from the mechanical to the, from the electrical to the mechanical, you will need a conversion, right? EG is one of them, and which is governed by the KV and the KT. KV is the electrical side, KT is the mechanical side. Okay, so for simplicity, we will ignore the frictions. Okay, of course we know that there are we have frictions. Even you put bearing, okay, they always have friction. And of course we have the TL, which is the load. Okay, so for simplicity on the mechanical side, right, we will just neglect it. Okay, for these calculations. Okay, so how this thing is applied, or how the DC drive is made. Okay, so DC drive, basically you can see, okay, this is your motor. Okay, this is armature side and this is your field side. Okay, we have a AC to DC converter, which is a control rectifier on one side, and the other side also the same, which is AC to DC. So you can control both the field and the armature, okay, at different firing angle, okay, at different firing angles. And then in terms of circuit, right, it will look something like that. Okay, we will have a very simple thyristor base, okay, control rectifier, which is applied to the armature, and then another, what we call this, yeah, control rectifier, okay, that is connected to the field. And equation-wise, okay, all right, is both are the same, okay, which is 2 Vm divided by pi cos your alpha, okay, and similarly for the field. Now bear in mind, this equation, right, 2 Vm divided by pi, okay, is meant for inductive load. If you go back and recall for this equation, okay, single phase, right, all right, 2 Vm divided by pi cos alpha, okay, is for inductive load. I forgot to record. Yeah. Oh, someone started. Okay. You all should inform me. Okay, so this is with inductive load. But if you are connecting to a resistive load, okay, like this one, the equation are different, so please don't confuse. Both also single phase full wave, but the equation is really depend on what type of loads. Okay, for resistive load, it's Vm divided by pi, and 1 plus cos alpha. Okay, that is for resistive load. You will get this result. And of course, for inductive load, it's 2 Vm. So in the case of application to the DC drive, right, we are applying this equation. If you apply this equation, then you will get things wrong. Okay. Okay. Okay, so just make sure that when you do the DC drive, okay, you have to use the right equations. Okay, so now straight away we look at one of the example from a textbook. Okay, let's say you are going to have separately excited DC motor controlled by a single phase converter drive, and the DC supply, okay, to the amateur is 250. This one actually I changed already. Original textbook is a US lah, so I just want to make it much more relevant to Malaysia. All right, and then the value of the amateurs, okay, is 0.25, and the field's circuit, okay, is 175 ohms. Okay, so these two values are given. The motor wattage constant kV, okay, kV is given 1.4 watt. So this is the conversion of the wattage to RPM. See, so a 1.4 per radian per second. And the torque constant, okay, again, like I said, most of the time they are same. Okay, that is on the mechanical side. Okay, that means at the shaft there. Okay, so these are the armature, and the shaft there is also 1.4 Newton meter per ampere. Okay, the Newton meter per ampere. So this is a very important constant. Okay, and assume, okay, all the physical friction is eligible, so we can make the equation much more straightforward. So let's say if the delay angle of the field converter is 0, means that you don't have any firing angle, you apply full power to the field. And then the amateur, okay, converter is 60 degree. Okay, so you reduce a little bit, 60 degree. And the amateur current will be around 40 amp. Okay, and determine the motor torque, the motor speed, electrical power, and mechanical power. Okay, of course, lastly, the DC drive conversion efficiency. All right, so to do that, okay, first of all, we need to find the peak voltage, which will be 230 multiplied square root of 2, you get 325. And then, we want to calculate the field voltage, right? So we apply this equation, okay, and cos this is 0 degree, and you will get around 207 volt that is applied to the field. And then with the known field voltage, so we can calculate the field current. Okay, so the field current is 1.18 amps. Okay, and then with the field current, then we can calculate the torque. Okay, KT multiplied by field multiplied by the armature current, which is given here 40 amp. So you will get the motor torque of around 73.34. So you answer the first question. Now you know that, oh, this is the torque. Okay, and of course motor speed. Okay, so you see the field control the torque. Okay, the armature control the speed. Okay, so when you have a separate excited DC motor, you can control them independently. Okay, whereas for a series connect, right? Because they are connected together. So basically, you cannot control them independently at certain point. Okay, it's a bit hard to control. Okay, because you change a bit, you change both. So for this one again, okay, the VA, you will use the same equation. Okay, but the firing angle now here is 60 degree. Okay, so 60 degree, then you will get this voltage applied to the VA. And then the back EMF, okay, 95, and with the back EMF, we can calculate, okay, the speed in omega, which is radian per second. It will give you around 56.6 radian per second. Or you convert to RPM, it will give you around 541 RPM. So you calculated the motor speed. And then the next one, okay, is the electrical power. So electrical power is pretty straightforward. Okay, the P equal to IV plus VF, okay, multiplied by IF, both add together. So this will be the power on the electrical side. I remember motor or machine is to convert, okay, electrical to mechanical. Okay, now our output is mechanical power, right? So mechanical power, okay, is TD multiplied by omega. We get around 4151. Now, from the number, you can actually roughly know whether your calculation is correct or not. Okay, as we know that there is no 100% efficiency, right? So your input will be always higher than your output. If suddenly you calculate and you found that your output is higher than the input, something is wrong. You will get more than 100% efficiency. Okay, so in this case, yeah, where our output is the mechanical power, our input is the electrical power, then we will have an efficiency of around, okay, 94.7%. Okay, so that should answer, okay, 1, 2, 3, 4 of this. Okay, electrical, mechanical, and also efficiency. Okay, pretty straightforward lah. All right. So up to this point, any question? But I believe you all should already study this in your electrical machine, right? So this is just more or less on the recap lah. Any questions? Hello, you guys there?
Yeah, no, sir.
Okay. All right. Okay. So maybe we'll do a little bit of simulating to see, you know, how we can get this thing, you know, work in a simulating model. All right. So the easiest way to do that, right, is just to, you know, after we calculate, right, we know that our VS is 207, our VA is 103. So when you have this machine, right, in simulating, this is a field. We just directly connect to a DC source, 207. And then the amateur, we connect to 103.5. Okay, you can put 0.5. All right. And then the input, right? This is not torque, actually it's RPM, sorry, it's omega. Because based on the calculation, we know that our speed will be around 56.6. Okay, so we set the speed, and then M is the measurement. Okay, so it will measure, okay, the first one here, 56 is RPM. Okay, this is the omega. Okay, this one is the IA, which is pretty much close, of 42. Yeah, the theory one is 40. And then this is the IF. Okay, 1.177. So it's 1.18. Okay, pretty much close. And then of course the last one is the torque, mechanical torque. So 70.61. So we have around 73.34. Okay. So how we are going to do that? Okay, so basically, okay. All right. So this is the easiest way to do it. Okay, of course, you need to find your motor. Okay, your motor in specialized power system under electrical machine. There's only one DC machine here. So just drag over. Okay, and then constant block. Okay, this one I should change to omega. okay, and two DC source, okay, and then yeah, the measurement you can put in the scope, or you straight away put a what we call this a display. Now the tedious thing or the hardest part is this one. First of all, yeah, we don't use any preset model because MATLAB already give you quite a number of preset model. Unless the model you know you are using, you can select them. But this one is from the textbook, so we don't have any preset model. And then field type we're using wound. They are permanent magnet of one because we got a separate right coin, so it's wound. And the mechanical input, okay, this one I think by default is torque. Okay, so we will put the RPM. Okay, we will put the RPM input, okay, to set the speed. All right, and then on the parameters, okay, now the field armature mutant inductor is basically the kV and kT, so we put 1.4. Now the trick is here, okay, the RA is 0.25, but the problem is that the L, we don't have the L information. Okay, we don't have the L information in the question. They just give us the RA, and there is no L information. So usually if there is no L information, so what we were trying to do is that we will just keep the default value. Okay, we just keep the default value. All right, so the default value is 0.012. We don't change, we just change the R. Similarly, okay, for the field, okay, we don't change the default value. All right, we don't change the default value. Okay, the rest, okay, no more. And then, yeah, you run it for 1 second. So if everything is okay, you should be able to get the quite similar result, okay, on this. Of course, this is just a scope to show the current. Okay, we always have, when the motor is running, right? Especially the armature, you will see it will take a lot of current, then slowly when you reach to the speed, okay, then it will be constant. Okay, field is always constant, okay, because it just feel right, it's not rotating. The armature is the one that rotating, okay, and of course the armature, okay, and the TD, okay, also same, okay, it start to rotate, and then torque very high, and then slowly it will settle at the what we call this constant, torque. All right. Okay. So yeah, you guys want to try this? This is the simplest already because the next one will be very complicated. I don't think we have time for that. But if you really want to try this, I'm not sure if you have done this in your machine, that is okay lah. Have you all done this in your machine class?
No.
Oh, no.
Just wish I can do this.
Oh, then maybe we spend 10 minutes. Okay, please do this. So at least you will see some relevant calculations. Yeah. Once you get this done, then post in the chat box. Then we will move on. Because the one with the the control rectifier is because you don't need to replace the battery with the rectifier. But I will show you lah. Okay, I will show you how it works. Okay, but just for the sake of for you all to try, play around with it. So this is very much more simple to construct. Okay, that is, yeah, the simplest I can think out of lah. So the component you need are also not much. You just need a DC machine, obviously the setting lah. Okay, and the rest is just DC constant and the scope. Okay, this one just put there, and yeah. Let me see, the solver I change, let's say if I use the automatic one, see if it works properly or not. Okay, if I use the automatic one, yeah, it will give us more or less the same answer. Let's see if I change this to. But usually people design, they will look at the RPM, okay, rather than the torque, because RPM is much more easy to measure. Yeah, more or less lah. You will see, even this one, right? The motor, like I said, the mechanical input, you either change to torque or you change to speed. Both should work. In this case, like I change to torque, right? So it's 73. Okay. Then you will see that, yeah, my RPM, current, it should be very close to the theoretical value lah. Unless you have to go really precise, 0.34, right? So if your model is correct, this one should be close to the model, the calculation. Yeah, 73. Okay, the torque here. So it's either you want to choose to have a set. I mean, it depends on if you want speed, right? You put RPM or if you want, so I don't want speed, it's not my interest. I'm talking about torque because my load is heavy or whatever. It's really up to you. Okay, which one you want to look at lah. So you can play around. I hope some of you will try with the torque. Some of you will try with the RPM lah. Slightly different here. Okay. So like I said, why the current a bit more different? Like I said, the information missing here is the inductor value, right? We only know the ohms. Okay. So if we have the detailed data sheet, we should be able to model exactly. Now you see the difference is that if you increase the torque, right, you can actually model much more detail on the frictions, column friction, and so forth. Okay, but if you model the speed, it's much more simple. Now I change back to speed. I apply, I come here, you see, nothing else. Okay, that's why most of the time people will model speed. Okay, this one 56.6, right? For the speed. Okay, right on 56.6, yeah. So to model the speed, okay. This one, it really affected the what we call the torque already. So we put 56 is much more. See, the sensitivity is actually dependent on the kV, okay, on the kV. Sensitivity of this kV, all right. Okay, so yeah, try to do that. It should be quite easy to do. So the main difference between the AC and DC drive is, AC drive, basically we use a DC-AC converter. We control the frequency, we control the speed. We control the wattage, magnitude, we control the torque, okay? And for DC machine, okay, we control the armature, we control the speed, we control the field, we control the torque. But in industrial, okay, the AC machine is much more common, widely used because of the simplicity as well as easy maintenance. Right, DC motor have one problem, is the brush. Right, they will have, you can see these are the two brush. So the brush will wear off from time to time. Okay, then, you need a lot of maintenance. And a DC machine also tend to be much more expensive, plus maintenance also expensive. That's why, unless it's deemed necessary, okay, that you would really need a very precise speed and torque control, then you only, even EV, we don't use DC motor. Okay, EV, we also use the AC machine. Otherwise, you need to service your car motor, But must be, I'm not sure how long, but it will be much more often. No? Are you guys working on it?
Yes, sir. So using the default software, is it?
This one, yeah, I use default. Lor. I use this automatic lah. Yeah, auto. So you can see if you use auto, right, it will select what for you is ODE 15S. So if cannot, you will select lah. Usually, if it doesn't work, I will select ODE 23. That is the best solver. Almost can run every simulation. Configuration of the motor, yeah, you just say no, and then you can change the speed, and it's much more easier lah. If you change torque, it will have, yeah, much more detail you can fill in, so that will affect your output lor. But like I said, even I myself don't really see DC motor being used in the industry. Maybe the industry I visit, I don't like this what we call semiconductor industry. They all use AC drive. Oh, okay. Some coming in already. Yeah. Okay, good. Plus minus lah, the value. Yeah. You won't get exactly the same as a theoretical because we also don't know how MATLAB actually model this model. They actually add a lot of things which will affect the output a little bit because of this detail. Wow, this one much more closer. You got 41 amps, 1.1. Okay, 67. Okay, so the solver sometimes also will give you slightly different result. When you change torque, yeah, it will really affect unless I found that the output is much more affected compared to the theory. That's why the easiest one is to go for the speed. Even most of the time, your car, they are measuring the speed, not the torque, right? We don't have a torque meter. We have the speedometer, we have RPM, right? Unless a very specific application. That's why if you change this to the torque mechanical, to the torque configuration, you see the parameter, it will end up with much more parameter. You must know what is the inertia. The inertia is also another thing very hard to determine because it depends on the shaft, how big the mass of the shaft, right? That will determine the inertia and the frictions and what is also the initial speed. So by default, you don't change, right? Of course, it will affect your output lah. So to make things much more simple, we just change to speed. Okay. So if question like that appear in your final question, I believe it's pretty much straightforward lah. Okay, you just need to, like I said, very important is that you don't get the wrong equation. Okay, you need to get the equations for the inductive load, not the resistive load. Okay, that's key point number 1. Okay, the rest is pretty much straightforward. Okay. So question like that can be easily around 10 marks because one of them is 1 mark, 1 mark, 1 mark, right? 1, 1, 1. And then I may ask you to, okay, draw the DC drive, you know, then you should know how to draw this lah. Okay, to draw this, maybe this one another 5 marks, I don't know. And yeah. Okay, so, okay, I think I need to move on already, otherwise not enough time. Okay, just save this thing. Oh, some Ajami, finally, yours one pop up. Okay. Okay. Oh, how come you get negative? Very strange, eh? Maybe you rerun it again or anything is that long. Otherwise, all your time is too short. Okay, you sometime right the motor. Remember motor? Last time I remember I simulate also. I found how come the answer is so weird. So I simulate longer time, like 10 seconds. Remember the motor when it run, right? It doesn't run straight away, right? It needs time to pick up the speed and the torque to get the final value. See, all the calculation here is the final value. It means your motor, right, is running at the steady state lah. So you may need to try, yeah, to run at a longer time. But mine was so far 1 second can. Okay, so all right, I think most of you have get it done. Let me just move on. Okay. All right, so this is the simplest way. Like I said, you know, we just calculate the wattage, we apply directly. Okay, but of course in real, okay, these are the setting. Okay, in real, it should look something like that. Okay, if you look at the, see one side we got one control rectifier at the other side, right? So you need to have two sets. You need to have two sets. So both also connected to the same AC source. So this will rectify, okay, it will rectify the and connect to the field. Okay, it will rectify and connect to the field. And then the other side also rectified, but this one the firing angle is the firing angle one is 0 degree. Okay. So this one is a 0 degree firing angle, and this one is 60 degree. Okay, 60 degree, which is if you want to calculate in pi, which is pi divided by 3 lah. Okay. Now, as we know that when we use this rectifier control, right, there are internal resistance and so and that. So your output won't be theoretical, okay? So you will see that I purposely put a wattage measurement that, okay, for this one, I still get 103, okay? And I calculate, I think it's 103.5 lah. And for the field, right, we have 205.8. So the theory one is 207, some wattage drop, okay, on the thyristor here. So, you know, it's okay, still acceptable within the range, And this one also the same, not the torque, RPM speed and the motor, okay. you will get more or less the same. Okay, there's one problem here for this motor. Again, like I said, the I value. When you use rectifier, right? Okay, it will affect, because this rectifier will affect the output. So we need to change. Okay, to change the inductor value. Okay, again, this is a guess value, because I also don't know what is the actual value. Okay, but we know that for the RA is always less than 1 ohm. Okay, RA, okay, is always less than 1 ohm, and then RF is, is always more than 1 ohm. Okay, one is always less than 1 ohm, one is always more than 1 ohm. That's why you look at their default setting. See, it's 0.012, and this one is 120, which is a bit too big, huh? So there is no other ways. I mean, unless the manufacturer tell you what is the Henry of this value. So I put a wild guess based on these understood rules, like, has to be less than 1 ohm, has to be more than 1 ohm. I just make it like divided by 10 and multiply by 10. So they both have to work equally lah. So by changing this to 0.1 and multiply by 10, okay, so I managed to get the output, okay, quite similar to the theoretical by using this. Okay, remember, because the output here is, the problem is because the output here is not a pure DC. Remember that when we do this, right, we put this, when apply the field and armature, we are using a pure DC. And our theoretical calculation will also assume the voltage and apply to the armature and the field are pure DC. But in real case of the control rectifier, it is not pure, right? We know that it is not a pure DC. So with this one, it will affect the output. So we need to, that's why you can see you cannot get exactly the same. The current increase a bit, this one also increase a bit. All right. Two factor, one is the inductor, unknown inductor value, unless you are given, or else it's just very simple, less than 1 ohm, more than 1 ohm. Okay, the armature is less than 1 ohm, the field is always more than 1 ohms. Okay, so if we do that in what we call this simulating. Where's my simulating? Okay. Okay. So we do that in the simulating here. Okay. So we can see that when we run, right, we will get the voltage. And let's say I just need to put the scope lah, so you will see actually, yeah, why and why it looks so different. Not say so different. Why you affect the result lah. Okay. Okay, so I just need to zoom in. Okay, one part of it. All right. So this is 0 degree. Okay, 0 degree, you will have this. So, yep, you'll get 205, right? Actual is 207 theoretical. Okay, to connect again, I should have put two, yeah. So that was the field, and this was the amateurs. Okay, I run in 1 second, so it will be slightly, yeah. Okay, you can see that it is, chop off, and you see what happened. Remember, this is an inductive load, right? You will have gone to the negative side. Okay, it will go on to the negative side. All right, so this is an inductive load unless you put a flywheeling. But most of these DC drive, right? They actually allow you to select, you know, you want to have with the flywheel or not, okay? So you can actually select for that functions. Okay, so all right. So that will give you 103. Okay, so we can actually set the firing angle here for both of these, which I already showed. This is just show the application of the control rectifier, okay, for the magnetic crane as well as the DC machine, okay, as well as the DC machine. So to simplify this one, so I made these two into battery. Of course, in real application, you will still see slightly difference, okay, slightly difference in between the, the value here, okay. All right. So with that one, okay, with this one, okay, this is a simplified version, which will give you a value much more closer to the theoretical. But don't be surprised when you work on this, you will see the value, hey, how come it's a bit off, okay? Because the voltage we supply is not DC, okay? So that will cause the slight difference. So likewise for practical application. Okay. Now, okay, industrial DC motor drive, okay, from the outside, you really can't tell whether it's an AC drive or the DC drive, okay. You really need to look at the, of course, the manual, okay. So these are some Siemens and ABB, of course, they have this, okay. So basically, it's an AC to DC converter that will power, okay, the DC machine, okay, control rectifier. And of course, it depends on the serial or the separate excited. Okay, so most of these industrial DC drive, okay, they allow you to configure, you know, all 4 different configuration. Okay, nowadays then a lot of setting you can do. You need to really go through the manual for that. Okay, so yeah, unless you are experienced, I mean, when you, the good thing you want to learn this is that you have to work in the industry. That will allow you to, you know, they have a project for you to install this. Then over the moment you want to install it, you need to learn, right? Then obviously you need to look at their manual and try to understand how to do the setting. But the underlying basic principle, okay, is what I have shown you in this, this what we call this diagram, okay. You know, some they straight away use a bridge rectifier. That means if bridge means that straight away you cannot control the field, okay? You cannot control the field. But of course, nowadays, most of the DC drive, right, they are control rectifier. So you are allowed to control the field as well as control the amateurs. So that's the purpose of this control rectifier. Okay. All right. So now so far, right, all these rectifier we see, right, is what we call it 6-pulse rectifier. Okay, because got 6 these are diode or thyristor, okay, for 3-phase application. All right. So these are just some of the okay, we have 12 pulse, 18 pulse, 24 pulse. Okay, all these applicable to only 3-phase. Now for 3-phase, most of the time, normal under normal condition, we only using the 6. Okay, but if we double up, right, we can connect in this way, so we can make 12 pulse. Okay, and we can triple up, right, and we can make it to 18 pulse. Okay, and of course, we can do that in 24 pulse. Okay, what is the advantage of doing that? Okay, the advantage is that, as we know that rectifier will actually causing harmonic problem to the grid. Okay, so the normal we use is only 6 pulse, right? You will create higher what we call this harmonic. So when you increase the number of thyristor switching, you indirectly reduce the harmonic. Okay, so the highest the pulse you go, the lower the harmonic it goes. Okay, so obviously even up to 24 pulse, they are still harmonic. It's just like it's not as high as the 6. So it depends on your application. Do you need to further reduce on the grid? Okay, so this is you see, it got two ways only, you know, to settle this harmonic problem. Either you solve it at the grid side, either you solve it at the power electronic side. So the power electronic side is here, you have to increase. Then of course the problem for using this is that the converter will be very much expensive because you double the bridge. So the price double. And if you are using definitely you're going to use a transformer anyway. Okay, then your transformer, instead of single winding, you need to have a double winding here. So this will, you know, from 6 to 12, you almost literally double up your price. Okay, if you go to the 111, even more. Okay, and the fourth one. All right. So like I say, in the industry so far, I see it's only 12 hours they don't go 18 already, because in terms of cost and economy, it's not feasible. I mean, you pay so much money, right? The number of harmonic you bring down just a little bit. Okay, so like I said, 6 and 12 pulse are most commonly used. So 12 pulse is commonly used at a train system. Okay, the DC train system, they are using 12 pulse. Okay, they are not using the 6 pulse, because the 6 pulse harmonic is much more higher. So that they actually, how they did is very simple. They calculate most of the industry, they're using a single tune filter. Okay, if the single filter is much more expensive, okay, then they will go for the 12 pulse. And then the single field filter they use is much more cheaper compared to just 6 pulse. So it really depends on the, this is after some intensive study, they found that 12 pulse is right in the middle. It won't reduce the harmonic below the standard, but you can save some cost, okay, on it compared to just using a 6 pulse. So I would say, to be very honest, personally, I only see up to 12 pulse. You don't ask me, sir, where you can see use 18 and 24. Malaysia, I don't see any at the moment. Maybe somewhere else, I don't know. Okay, but 12 pulse, yeah, your MRT system is using it for sure already. Okay, and some of the train, okay, as well. And then like I say, like industrial applications, okay, even the HVDC, okay, is 12 pulse. Okay, they don't use more than that. Okay, train system, okay, and so forth. This is how it looks like in the real rectifier. Okay, in a big cabinet. Okay, these are all house the rectifier. These are some of the model you can download from Masswork, okay, done by one of our students. Okay, so this is to model the Malaysia Electric Railway DC 750 watt traction power, which is actually used in our MRT line and the Putra line and so forth, most of the urban. Okay, so in Malaysia, right, the incoming is 33 kV, okay, the MV voltage. So when it go to the station, these are actually housed inside the station, but remember, not every station have a TPSS. Okay, so they will actually, I think the one near UM1 got one. Okay, you can look at the map. Okay, actually you will see that they will have one of the point, not all. Some big station only have a small station, they don't have it. So again, like I said, you need to have a rectifier transformer. The transformer there will have 2 winding output, so that you can connect to a 12 pulse rectifier that will produce a DC 750 volt, so that you can connect it to the train system. So the train actually pick up, okay, the DC voltage 750 from the rail. The rail is powered by the station. So that's mean the whole thing here. The whole thing here, okay, is the station. Okay, it's the station. Okay, and then it connect to a number of stations, maybe not the next station or 2 or 3 stations, they will have another, what we call the TPSS, so that they will actually share the power. All right. So from here you can see the output of VDC. Okay. Okay. Of course you have to click what to see what is inside. Inside here is actually two rectifier that will give you a VDC of 750. You all can download this. Okay, you can download this and you can see what's inside. Maybe let me check. Do I have this or not? Okay. Okay. So of course, yeah, already make all the blocks inside here. When you open up, you actually see two set of thyristor. Okay, you will see two set of thyristors, so both connect in parallel. You make up of 12 pulse. So these are the controllers. Now you can see we have the pulse generator, thyristor 12 pulse from MATLAB already. That means you can straight away get it from here. And it's a feedback control. Okay, with the PI control, then you can control the output to exactly the set voltage that you want on 750. Because the train move, right, is not static. When the train moving away from the station, right, so the current it takes will become lower. Okay, it will become lower, then the voltage will tend to increase. And when the train are coming to the station, right, so the current will increase because it takes more current when it comes to the station. So it will also, it will reduce this voltage. So the PI controller is here to actually control to make sure that I don't care when the train come or go or stop, okay, or the train stop from one to start, it draw a lot of current, right? When it draw a lot of current, the voltage will also try to go low. But with this control rectifier, right, it will always maintain at 750 watt. So these are some of the real applications, okay, for this three-phase, okay, what we call this rectifier, okay, which is literally AC/DC converter lah. Okay, yeah, you can download this, from this one, so you can start to play around with it. Okay, oh, 6:00 already. Yeah, one more last class to go. I know, so maybe I need to be a bit faster. Okay, now, so far we have gone through rectifier without any filters. Without any filter, right? Be it the diode rectifier, be it a control rectifier, right? We just control the voltage. There's no filter to do the smoothing. So now we move on to the filters. Okay, basically for any rectifier, there are only three options of filters. Okay, one is the L only filters. One is the C only filters. And the last one is the combination of both L and C filters. And out of these three, okay, C filter is the most commonly used. First of all, because it's easily available. You buy capacitor, it's much more easy, right? All the value, they are there. Inductor, very hard. You either need to custom make, okay, and so forth. So capacitor is the easiest solution. And the combination of both of them give the so-called a better smoothing, all right? That now the capacitor, like I say, is a very common solution, but it also, I mean, both filter also got problem, like all three. They are actually the main culprit that will cause harmonic to the grid. Okay, so in other words, it will make the harmonic worse lah. Okay, you see, electronics or power, right? You cannot really find one solution that serves all. When you have one solution, this side you create another problem on another side. So that is the challenge of being an engineer, all right? But anyway, let us just look through the rectifier filters. Okay, so filter basically like, charge, discharge, charge, discharge. It's trying to smooth out the output instead of giving you this very, very high ripple. In other words, it reducing the ripple voltage. Okay, it reducing the ripple voltage. So governed by a very simple equation here. okay, where R is your resistance, C is your capacitor. So when you move around the equation, right, okay, what you need to know is that, okay, how much ripple factor you want your rectifier to be. And the rest is, you know, these are the main, I mean, among these three, this will be the main equation, okay, for you to actually calculate the capacitor that you need, okay. Then, of course, you will see that this equation, right, will affected by R. Okay, so if your R is constant, that is okay. If your R is constant, right, but remember there are many loads, the R is not constant. Okay, so when the R is not constant, then you have to try the two values, the highest and lowest. Okay, the highest and lowest, then you will try to see which one will give you the best result. Okay, if you are using only a capacitor filter, right, it's quite straightforward. The higher the better. The higher the better. Of course, at certain point, you may have some overshoot of voltage, so you just have to be careful on that. Okay. So how to find that? Okay, of course you have to find the minimum load and the maximum load in between. Then you can get all. This one has to be fixed. Okay, this one has to be fixed. Then you will get two value of this. Then usually we will find the one in between. Okay, there's no fixed rule. Okay, how you want to, because you are the one who decide the ripple factor. Okay, and of course at the end, right, the capacitor, whether you want to install, it depends on the client. If your capacitor is so expensive, they say, hey, I don't want can. And then you have to adjust a bit, sacrifice a bit of the ripple factor to get a lower value so that your client is willing to pay. Okay, so let's look at one of the text, this one again from textbook. So 120 volt, okay, obviously it's textbook, 60 hertz. Let's say your load is 500 ohm. Okay, and then you determine the capacitor filter. Okay, so that the ripple factor is less than 5%. Okay, it's less than 5%. So again, all right, we know the, the substitute, very straightforward. Substitute the value, you will get your capacitor value. And then with that, you can calculate, okay, your VDC. Okay, you can calculate your VDC, okay, based on the load and the capacitor value, and you can find this VDC. So it will slightly affect your VDC, okay, with your capacitor value. And your capacitor value, it will be affected by your ripples, okay, by your ripples. You will notice that the lower the ripple factor, the higher the capacitor value you have. But this capacitor is not a small capacitor, okay? For industry, big capacitor, it costs a lot. Of course, if you are designed for a small rectifier, then it's okay, it's 20 cents only, right? So it doesn't really matter. Okay, so here are some of the examples, okay, where we have a, what we call this a capacitor, right? So we will see that the value is 158, which is correct based on the calculation. Okay, so this will be the output. Okay, you will have some form of these are the 5% of this output. Okay, then of course the problem is the current. See, the problem is the current. So the current will be very spiky. Okay, because every time, right, when they go down, it charge. Okay, it will draw a lot of current. So this is the main culprit that will cause harmonic at the grid. Okay, small power supply is okay, like the one we use for our handphone charger, no issue lah. The harmonic are so low. Okay, so that will actually tell you it does not draw the current in a linear form. Okay, so that is also the main reason. Okay, that will, it will cause harmonic. Like I say, low power is no issue at all, especially at LV. LV 400 watt and below, it's not. You connect 10 computer also no issue. Okay, but remember when you're dealing something with MV, okay, that is issue because MV will directly affect the grid. And TMB mandate that, okay, the THD cannot be more than 5%. If it's more than 5%, right, they will never approve during your, they don't even allow you to commission. If you show them, say, hey, saya punya harmonic 6% boleh tak? I tell you, they give you middle finger, say no. You do not even can commission the thing. You have to solve it first. Okay, so it's pretty straightforward. Okay, you can just try this. Okay, capacitor, resistor. This one, this is just a bridge, no firing angle result. You can fill in this value. Of course, this is RMS. You have to convert it to peak. I think it's 170 if I'm not mistaken. So you should be able to do this one quite straightforward. Okay, we move on first. We see got enough time or not, because yeah, we just have one more class to go. Okay, so that is the capacitor filters. So the next one will be the inductor. Okay, the inductor filters. So inductor filter again, you can based on these equations. Alright, then you can just move the L out and ripple factor in, so that you can actually calculate the inductor. Okay, for your what we call these filters. So again, a serial inductor, right, offer a high impedance for harmonic current, so it also help reducing the harmonic. Okay, but the problem with the inductor is that high impedance, so it also reduce the output voltage. Okay, so it also introduce a time delay for the load current with respect to the input voltage. This is also another reason why most people don't use inductor or for these filters. Okay, but again, let's try again with the same source, same load. Okay, but now same harmonic ripple factor. Then, but this round we calculate the L. Okay, so this will be the equations. All right, and then you calculate the L, you will get 6.22. So you have to work this out. Okay, I show you the answer already. And then with this one, we calculate the IDC. Okay, and of course you can see that the VDC is 108. See, you compare to the capacitor one, right? The capacitor give you 158. So 50 watt difference. Okay, with the same harmonic factor. And of course, in terms of cost and availability of the filters, capacitor is much more easy. Okay, but of course you have higher harmonic Okay, so again, when we change this to the inductor, okay, you can see that the voltage go low. Okay, but you will see that now this is the output voltage, and this is the output current. Okay, so it's much more linear compared. Linear means that the voltage and current are the same. Okay, non-linear means that the voltage and the current look totally different. Okay, we call a non-linear load. Okay, because Ohm's law tells us that the voltage and current, right, you apply to a linear load, which is a resistor, there should be the same in terms of the pattern, not the value. Okay, the value depends on the ohms. Okay, but this one you can see is totally non-linear because the draw of current is totally different from the voltage. So for this one, okay, you can see the draw of current will be similar to the draw of the voltage. So this is what we call linear load, okay, and non-linear load. Okay, so these are the standard terms. Okay, three-phase. Okay, let's move on the three-phase first. I think. Okay, now both two method, right, I show, right, is a single phase. Of course, when you want to combine both, you just put this, the capacitor here, you combine both, increase the cost. Okay, so you get the in between. All right. Now we move on to the three-phase rectifier. Okay, this one I also show the combination of both. Okay, so governed by equation of this one is 6 pulse, a normal one. For 12 pulse, okay, you have to use a different value. Okay, for 12 pulse, it's a different value. And they use what we call a ripple ratio rather than the ripple factor, okay, for 3 pulse, all right? So the difference is that, yeah, we usually use the FC and FR, okay? FR is the ripple frequency. SC is the cutoff frequency, which is around 50 Hertz to 1000 Hertz, all right? So along this value, it should work lah. And then for the ripple frequency is 6 pulse, right? So it's times 6. Okay, for 12 pulse, you just times 12. Okay, for this one. So with this, okay, let's say assume 50 or 1000 and you divide by 6 pulse, 300 and square, then you will get the IRR. Okay, so when you get the IRR, you substitute in here, then you can calculate your L. Okay, you can calculate your L. So when you must calculate your L first before you can calculate your C. All right. Then after you get your L, then you just substitute into this equation to get your C. Okay, to get your C. So the difference for L is only here. Okay, 12 pulse. I say I don't really see actual 18 pulse yet lah. I believe they are lah, somewhere lah. I don't know, in Malaysia or other country. So my knowledge limited to only 12 pulse, okay, but we do know that there are 18 and 24 pulse out there. Okay, so after that, we can, yeah, so this one is a 3-phase, okay, so we can connect them, and then you can see that it will give a much more smoother output, okay. Much more smoother output. Of course, this one we can zoom in. This is the small ripple, okay, for 3-phase. Then for the current at the rectifier side here, right? Of course, again, it still produce harmonics, okay. It still produce harmonics. Let's see. We can. Oh, this one, okay. I think okay, done already. The next one will be next week class. Okay. Let me just show you all this. Oh, no, not this one. Drive, okay. Power electronics. Okay. All right. So yeah, 390, 12. I mean, you can do your calculation. Okay. I try 50 Hertz, 100 Hertz, and 500 Hertz for the cutoff. They all work. Okay. They all work. Okay. So this is. Okay, so it's quite smooth, I would say. It's quite smooth for the output. And then for the AC side, right? Okay, this one is a problem for 3-phase. 3-phase will get, like, for example, both, if you look at the voltage and the current, you will notice that, right? The voltage also been affected. You can see that it's also been affected badly. Okay, for single phase, the voltage doesn't really affected that much. And you can see the current, right, is no longer sine wave. Again, I say, when the voltage and current, okay, are different, they draw current differently from the voltage, means it's a non-linear load. So it will cause harmonic, okay, to the grid side. Okay, and like I say, it depends on the power. LV, no issue. Okay, a lot of LV, they don't have this problem. But for MV, okay, you have to be very careful. Now, if I take examples that let's say, I just put a capacitor. I remove this one. Okay, and slightly increase a bit. Okay, 120. Okay. So this is what happened. Okay, you can see ripple is much more higher because of the absence of the inductor. Okay, and it has a bit of overshoot. That's why three-phase is always used combined. Single phase is okay. Single phase you don't use either one of them will do. Okay, for three-phase you have to be a bit careful. You want to save money also can, but you have to be aware you will have a little bit of shoot up, overshoot, and then of course the harmonic also look very much different. Okay, now you can see that they will have what we call a rabbit ear harmonics. Okay, if we zoom in. Okay, this is what we call wattage notch. Okay, wattage notch, and we have that means the harmonic is much more serious than the one with the what we call with the inductor. Even with the inductor, there are harmonics. Okay, but it helps to smooth up a bit so that when you apply filter, right, your filter power is lower, it's cheaper. Lor. If you don't do that, then your filter to solve this problem will become much more expensive. All right. So the filter design is actually on the topic of power quality, which we will not cover here, but I will cover the active front end and power factor correction in the next class, how we can use power electronic means of solving this problem. Okay, so you can see that very, totally not acceptable. If you connect to MV, sure you cannot connect, but LV is still acceptable. But again, if LV, right, especially on the big building, when there are so many, the factory building, when they have a lot of big machine, but they are connected to LV, okay? But all the machine, they produce all this type of harmonic can causing problem also. Commercial one don't have much. Commercial shopping mall, we don't really have much of this problem. Okay, we don't have much, but factory, even a small factory, they might have this problem. Okay. All right, so okay, so yeah, if I put back, then of course, yeah. Okay, let me just open this again. Okay, so if I remove the capacitor, put only back the inductor, you will see actually it's much more smoother, right? Exactly same like the one. Okay, but of course the wattage is decreased lah. Okay, and okay, and this is the wattage. Okay, yeah. So different filter will give you different outputs. Okay, so in other words, three-phase filter, inductive is much more favorable, especially high power. For single-phase filter, capacitor-based filter is much more favorable. Okay. So sometimes you go to work, right? The engineer won't tell you why one. So this one I use inductor in reactor-based filter. This one I use capacitor. You ask him why. Many times they will tell you, oh, my senior tell me one. When you look at this, you do this. I also don't know why, but it works. So in fact, many of these types of question or problem in the industry has been taught in the textbook or during the class like today. But I believe after final exam, most probably you all will forget about it. Maybe after 2, 3, or 4 years, when you work in certain project that have this, then you ask, hey, how you know? Sometimes really, they look at those experienced engineers. Some they really know why. Some they don't know because they just follow the senior. The senior will just teach them, oh, when you have this problem, right, you just change this reactor, you will solve it. Then you change and solve. They go, wow, so king, you're so king, But sometimes you have to, hey, why? They also say, don't know, my senior teach me one. So they follow. Sometimes in a company, they just say they have a special SOP to show that, okay, when you design for this project, right, you don't care. You just follow this, will do. Which is actually happening in Malaysia consultancy firm. many of them are actually, because they work on the project for so many years, they know already the solution. Okay, so you just follow without really knowing why. Yeah, but I say like, okay, things has been taught in a textbook. Okay, so it's important that you have to relate what you learn in the textbook to the industrial practice. Okay, yeah, because you see, industry will always say, the new graduate have no idea what is that, because what you all see is all textbook thing. Okay, then how is it related to the real industry? You have no idea. So there is actually a gap over there lah. Okay, so from what my experience is that, like I said, that's why I always encourage you all do simulation. This is the only way you can bridge the gap to let you know why. Okay, because nowadays, simulation software are available. Imagine my time when I study, right? No simulating, already got MATLAB lah, but no simulating first thing. Simulating came out in the early 90s, but there is no power system toolbox. We have to do things very, very manual. Have no idea at all how this thing works. Okay, of course, it's all based on textbook, lor. But you see, nowadays your generation is pretty much blessed with simulation software, so you can actually test a lot of things to reinforce your understanding. What happened when we add this, when we change this and that. All right. Okay. Yeah, I think pretty much done. Okay, so the rest we will go for the last class. Okay, but in fact we got time. It's actually good to do these filters lah. But I believe yeah, if you got time you can do it on your own. Okay. Okay. Any questions?
No, sir.
Okay. All right. Very good. Yeah, if no question, then we will end the class today. Okay, it's already 6:30.